Welcome to this last lecture in the 7th week of our course Analysis of a Complex Kind. In this lecture, I'll show you how to evaluate an improper integral via the residue theorem. This is a real valued integral that doesn't look complex at all, and it's very hard to tackle using methods from real analysis. But it turns out by turning to complex analysis, we can actually find this integral. Here's the integral we want to evaluate, the integral from 0 to infinity cosine x over 1 plus x squared dx. You can try all kinds of substitutions and techniques you know from calculus, but it's really, really hard to crack this integral. Let me quickly explain what all this notation means. First of all, when we write the integral from 0 to infinity, what that really means is we're taking the integral from 0 to r, where r is some large number, and we're letting r go to infinity. And so we need to consider the integral from 0 to r of cosine x over 1 plus x squared dx. Again, this is a real valued integral, an integral on the real axis. And then we need to let r go to infinity. Here's the next idea. The integral from 0 to r of this function cosine x over 1 plus x squared is half of the integral when we go from negative r to r. The reason is that the function cosine x over 1 plus x squared is an even function. Look at this picture. Here you can see the function cosine x over 1 plus x squared from 0 to 10. The integral of this function is the area under the curve, where areas above the x-axis count as positive and areas below the x-axis count as negative. Now look at what happens when we take the integral from negative r to r instead. You see the function is symmetric, and so exactly the same areas are added up to the left of the origin as there are to the right of the origin, so that when I integrate from negative r to r instead of from 0 to r, I get twice the value of the integral. So instead of integrating from 0 to r, I might just as well integrate from negative r to r to make things more symmetrical, and then divide the result by 2. Here's the next idea. I can add an extra term in the numerator. The extra term I just added is I times sine x, and the claim is that didn't change anything. Why is that? Let's look at the function sine x divided by 1 plus x squared. That function is an odd function. Look at this picture. For the function sine x over 1 plus x squared, when I integrate it from 0 to r, I get the opposite value of the integral that I get when I integrate it from negative r to 0, because the function is odd. Whatever used to be above the x-axis is now below the x-axis, and vice versa. Areas to the left cancel out with areas to the right, so that the integral from negative r to r of sine x over 1 plus x squared dx is equal to 0. Now if I multiply this in addition by I, that doesn't change anything. Multiplying by I simply multiplies 0 by I, which is still 0. That's why I can simply add I times sine x to the integral here. But cosine x plus I sine x, that's equal to e to the ix. And all of a sudden, I get my exponential function into the picture here. So instead of finding the original integral from 0 to r of cosine x over 1 plus x squared dx, I might just as well find 1/2 times the integral from negative r to r of e to the ix over 1 plus x squared. Here's the next idea. This integral from negative r to r of e to the ix over 1 plus x squared dx can be written as a complex contour integral, namely as the integral over the line segment from negative r to r of the function e to the iz over 1 plus z squared dz. Why is that? This line segment from negative r to r in the complex plane can be parameterized as gamma of x equals x, where x goes from negative r to r. Then the derivative of this parameterization is simply 1. And so if I plug into this contour integral that parameterization, this becomes 1/2 times the integral from negative r to r of e to the I, and now I plug in gamma of x for z, but gamma of x is simply x, divided by 1 plus, and again for z I plug in gamma of x, but gamma of x is x. And then I need to multiply with the derivative, gamma prime of x, which is 1, and take the integral dx. But that's exactly the integral that we actually wanted to find. So the integral we want to find can be written as a complex contour integral. And that's what we want because ultimately we really want to use the residue theorem. Currently, we're simply integrating over a line segment. We're going to have to integrate over a closed curve in order to be able to use the residue theorem. So here's the next idea. This is the closed curve over which we're going to integrate. We're going to first integrate over the line segment from negative r to r and then go around this semicircle from r to negative r. So that's our curve CR. CR is the line segment together with that semicircle gamma r. But that's clearly not the same thing as what we wanted before. We really only wanted to integrate over the line segment. So if we integrate over all of CR, which is the line segment plus the semicircle, then we need to subtract the integral over the semicircle afterwards in order to make things right. And that's what we're doing right here. Now the great thing is, what is the integral over the curve CR of the function e to the iz over 1 plus z squared? E to the iz over 1 plus z squared has two singularities that are isolated. And the two singularities happen when the denominator of this function is equal to 0. When is the denominator equal to 0? When z is plus or minus I. Only the singularity at I is enclosed by the curve CR. The other singularity at negative I is down here, and we don't really care about it. Now, by the residue theorem, the integral over CR of the function e to the iz over 1 plus z squared is 2 pi I times the residue of my function at the singular point. So here we have 2 pi I times the residue of my function at I, and the 1/2, of course, had to stay there. And then we need to subtract this integral over the semicircle. So we have two things to do. We need to find that residue of the function e to the iz over 1 plus z squared at I, and then we need to take care of the integral over the semicircle. First, we're going to find the residue of e to the iz over 1 plus z squared at the singular point I. We notice that we have a simple pole at z equals I because 1 plus z squared factors into z plus I times z minus I. Therefore, the residue can simply be found by multiplying f by z minus I and then taking the limit as z approaches I. When I multiply f by z minus I, that z minus I will cancel out with this other z minus I in the denominator. And all that is left is then the z plus I. So I need to find the limit as z approaches I of e to the iz over z plus I. I find that limit by simply plugging in I for z. When I plug in I for z, I have an I squared in the exponent of the exponential function. So that's e to the negative 1, and the denominator becomes 2i. So that also is equal to 1 over 2ei. Therefore, the integral over the closed curve CR of e to the iz over 1 plus z squared dz by the residue theorem is 2 pi I times the residue, the 1/2 we need to carry around right here. Here's the 2 pi I, and here's the residue, 1 over 2ie. I can cancel a few things out, so this 2 and that 2, for example, this I and that I, and I'm left with pi over 2e. Next, I need to estimate the integral over the semicircle gamma r of my function f. Remember, gamma r was simply the semicircle of radius r centered at the origin. Plus, we're only really interested for what happens when r goes to infinity. What we want to show is that the integral actually goes to 0 as r goes to infinity, so it doesn't really matter at all. In order to show that some complicated expression goes to 0 as r goes to infinity, it really suffices to show that the absolute value of that complicated expression is bounded above by some constant for which it is easier for us to show that it goes to 0. So as long as this constant goes to 0, this integral, which is stuck between 0 and this constant that goes to 0, then is sandwiched in between 0 and the constant, and therefore has to go to 0 as well. So we're going to try to find an upper bound for the absolute value of the integral and show that upper bound goes to 0. And then the integral is forced to go to 0 as well. We need to show that the absolute value of the integral is bounded above by a constant where the constant goes to 0. How do we estimate the absolute value of an integral? Remember what we learned a while ago. The absolute value of a contour integral is bounded above by the length of the curve over which we're integrating times the maximum of the absolute value of f for z's that are on the curve. So let's use that. So therefore, in our case, the absolute value of the integral over gamma r of the function e to the iz over 1 plus z squared is bounded above by the length of the curve gamma r, and that's pretty easy to find. The length of the curve gamma r, it's a semicircle of radius r, so it's pi r, times the maximum of e to the iz over 1 plus z squared. So how do I estimate that? First, I need to look at the absolute value of e to the iz. Let's write z, that's x plus iy. Then e to the iz becomes e to the ix plus I squared y, so minus y. Now remember, the absolute value of e to the something is e to the real part of the exponent. But what is the real part of ix minus y? The real part of that is simply minus y. So the absolute value of e to the iz is e to the minus y. The denominator is simply the absolute value of 1 plus z squared, and here we use the reverse triangle inequality. The absolute value of 1 plus z squared is greater than or equal to the absolute value of z squared minus the absolute value of 1. The absolute value of z squared in that semicircle is always equal to r squared, and so the denominator is bounded below by r squared minus 1. Since it's in the denominator, we found that 1 over the absolute value of 1 plus z squared then is bounded above by 1 over r squared minus 1. And that's what you see right here. So the absolute value of my integrand is bounded above by e to the minus y divided by r squared minus 1. Now remember that we're only looking at the upper half of the circle of radius r centered at the origin. So all my z's are from this upper half of the circle, which means the y value of all of the z's is greater than or equal to 0. Because the y value is greater than or equal to 0, all these exponents minus y are less than or equal to 0, which means e to such an exponent is never greater than e to the 0, which is 1. Therefore, on the curve gamma r, the integrand is bounded above by 1 divided by r squared minus 1. So we have seen that the absolute value of the integral is bounded above by the length of the curve, which was pi r, times the maximum of the integrand, which was 1 over r squared minus 1. And what happens to this product as r goes to infinity? Well, the denominator goes to infinity much faster than the numerator. R squared wins over r, and therefore this whole fraction, pi r over r squared minus 1, goes to 0 as r goes to infinity. And that's what we wanted to show. Therefore, the integral of e to the iz over 1 plus z squared over the curve gamma r goes to 0 as r goes to infinity. Now it's time to put it all together. Remember, we wanted to find the integral from 0 to infinity of cosine x over 1 plus x squared. Here's what we have. We first realized that instead of taking the integral from 0 to infinity, we need to take the integral from 0 to r and then let r go to infinity. Next, we realized that instead of taking the integral from 0 to r, of cosine x over 1 plus x squared dx, we can turn this into something complex, namely integrate over the function e to the iz over 1 plus z squared. We integrated over the whole curve CR, which consisted of the line segment from negative r to r and the semicircle gamma r. Next, we showed that the integral over the closed curve CR of e to the iz over 1 plus z squared dz is 1/2 times 2 pi I times the residue of the function at I, and that turned out to be pi over 2e. So this integral right here, that evaluated to pi over 2e. Next, we showed that the integral over gamma r of e to the iz over 1 plus z squared tz goes to 0 as r goes to infinity. So this integral right here, that goes to 0 as r goes to infinity. Therefore, as r goes to infinity, this integral here converges to pi over 2e, the value of the first integral over CR, because the second integral simply goes to 0. And so we have just shown that the integral of cosine x over 1 plus x squared from 0 to infinity is equal to pi over 2e. This is a fabulous result, as the outcome of the equation includes some of the most important mathematical constants, namely pi, 2, the only even prime number, and e. I hope you enjoyed this course. It's been a pleasure teaching you all.